I left off in the last video finishing up with the probability table, and the last probability model type is the probability tree. It's nice because if there are more than just two events, you can add on another layer of branches and calculate 3 events. So it's a nice way to organize information. So that gave the overview of our organized lists, our tables, and our tree diagrams. And we're going to talk now about compound events and then some simulation. So with compound events, it's pretty important to start with an understanding of what are independent events and dependent events. Many students get stuck on those and they feel like one thing could affect another. One example is sisters. They're determining which of them should wash the dishes, so they come up with a system. They're going to flip coins. If Rachel gets heads, she does the dishes, and well, if it's heads, Rachel does the dishes. If it's tails, Christy does the dishes. So the question then, is this fair? Well, students pretty intuitively and quickly can figure out, well, that theoretical probability for heads is 1/2, and for tails it's also 1/2. So if you take a look at a situation after 1 week, Christy has washed the dishes 4 times and Rachel has washed the dishes 3 times. Christy feels it's not fair. She's done the dishes more often. Well, it's an odd number of times to do the dishes, so how can it be split evenly? It's impossible. But after 2 weeks, Christy has now done the dishes 10 times and Rachel has only done the dishes 4 times. So is this still fair in light of this information? Well, it's not very likely. So after a lot more trials, things should even out a little bit more. Now, an event like a situation like this tends to cause students to feel that the coin flipping, the idea that it's still 50-50, that the previous flips will affect the future flips. And they get that idea of independent versus dependent mixed up. They get this sense, this feeling that the previous events affect the future events of the coin flip, the coin toss. So that can be a little tough to smooth out. So because Christy is unhappy with the situation, she's going to suggest a little bit of a change. So Christy proposes to change the rules. She proposes that they get 2 coins, and each day she and Rachel will each take a coin and they flip at the same time. If the coins match, Chris will wash the dishes. If they do not match, Rachel washes the dishes. So Rachel thinks, hey, this is a pretty good deal because there's 2 ways for them to match, both with heads and tails, and only 1 way for them to not match. So when I did this with my class, because of that statement, they were pretty convinced that it was not a fair game until we looked at a systematic list of the different ways that the coins could turn out. So we talked about, well, what if one is a quarter and the other one's a penny? And both the quarter and the penny are heads. And then what if both are tails? So we've got those situations. But then we could have the quarter as heads and the penny as tails, and then the possibility of the quarter being tails and the penny being heads. Oops, all of a sudden we've got 4 possibilities. 4 of them match. I'm sorry, 2 of them match, 2 of them do not. And so that's 2 out of 4 in either direction. And again, 50-50. So it's still a fair game. Game of rock, paper, scissors. Is this a fair game? Kids like playing it, and we can talk about independent and dependent events. What are the 2 events? Well, in each game there are 2 players, and each player's choice is an event. So there are 2 events in this game, and they are independent of each other, assuming nobody goes before the other person, and the other person doesn't have a pattern. So we're going to assume that they are independent. So is it a fair game? And how could you list all of the different outcomes? This choice is rock. We can have rock, 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 paper, rock, scissors. So if we could keep up with a systematic list, maybe the first person's choice is paper, and the second person's is paper, rock, paper, 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 scissors. And then if the first person's choice happened to be scissors, then we can have rock, paper, scissors again for the last choice. So, is this a fair game? Well, each of these would be considered a tie, so they do not count. And then we can say person 1 wins in several of these cases. So person 1 wins the rock over scissors, the paper over rock, and the scissors over paper. And person 2 would be winning the others. So we've got 3 out of 9 wins for person 1. And 3 out of 9 wins for person 2. This would be a good place to yet again ask students, so if we played this game, say 12 times, how many times would you expect person 1 to win? Or how many ties would you expect? That kind of thing. Next up is this great game called 10 O's, where we make a number line, and students have 10 O's that they can place any place on this number line that they wish. From 1 to 12. 4, 5, 6, 7, 8, 9, 10, 11, and 12. So I could put an O here, and I could put one there, and I could put one there. It's sort of like bingo. So I'm going to roll a pair of dice, and each time I hit a sum that is represented on here, then we get to cross out an O. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I've got an extra one. Alright, so that was a pretty good one to get rid of, actually. So students can, try their hand and see who wins. So how could we investigate? Well, what if we start listing the possible outcomes? If I'm rolling 2 number cubes, is there any way we can get a 1? Nope, I don't think so. So, because we're adding them together, so I could get a 1 and a 1, that's the smallest amount I could get. I could get a 1 and a 2, and a 1 and a 3, and a 1 and a 4, and a 1 and a 5, and my list gets pretty long, and it gets a little messy. So, we come across, well, what about this idea of using an array to build this? So I could go like this. And very quickly, students can see just how many different outcomes we can possibly generate, because they're pretty good at area. And alright, we've got 36, and then we can put our sums in here. So I've got 2 and And here we are. Pretty quickly we can find out the probabilities of each of these occurring, and students want to play again because they'd like to put their O's in different places, because it's perfectly acceptable to put more than one O above a certain number. And as we can see, the greatest probability here is a 7. So we've got 1, 2, 3, 4, 5, 6 out of 36 is our probability of rolling the sum of 7. So probability of sum of 7, 6 out of 36, reducing to 1/6. This sample space all drawn out, we can ask some pretty weighty questions. We can start talking about some compound events with students. We can ask something along the lines of, well, what if I'm happy with rolling a sum of either 4 or 7? I'm happy with 4 or 7, either or. So that would be finding the probability of rolling 4 or 7. So how many am I happy with? I'm happy with 1, 2, 3 for the 4. So I'm good with 3. 3 out of 36. And I'm also happy with 1, 2, 3, 4, 5, 6 out of 36 for the probability of 7. So if I find the sum there, 9 out of 36, I'm perfectly happy with. So that gives us how to find one of our compound events. If we are finding the probability of either one event or another event that has nothing in common with the first, they are independent events, then those probabilities can be added. You add their probabilities. So using the example of a deck of cards, if I draw a king or a queen from a deck of cards, probability of drawing a king would be 4 out of 52. Probability of drawing a queen would also be 4 out of 52. So the probability of drawing either a king or a queen is the sum of those two, and then reduces to 2/13. So next week we'll talk some more about developing the idea of both one and the other event occurring, which actually is multiplication. So we're going to pick up next week, talk about, expand on finding compound events when we're looking for two events occurring, and also some computer simulations and tree diagrams and some other things. So we'll take another week on some probability. Okay, I hope you all have a great week, and see you next week. Bye.